In this video, we're going to talk about the area of a surface created by revolving some line or function around a specific axis. In this video, we're going to talk about the x-axis. In a future video, we'll talk about the y-axis, a revolution about the y-axis. So as long as we have a function that's positive, greater than or equal to 0, continuous and differentiable on a closed interval, which, we say that about everything. We say it's got to be continuous, you have to be able to take the derivative, etc. Interval is closed. All of that, that's pretty standard. But the function needs to be positive, so above the x-axis. The area of the surface created by revolving that curve, a line or a curve shape, about the x-axis. So we're talking about a shape maybe like this, and what happens when I revolve that about the axis, I would get kind of like a vase shape, if you will, right? If I took it and rotated it about here. We're not finding the volume, we're finding the area of that surface that's created. So let's think about how we would do that. Let's think about our surface area formula here. We have our closed interval A to B, that's our horizontal region, right, from A to B. And we have 2 pi times some function. That function represents the radius. And if you think about 2 pi r, that represents circumference. So basically that is calculating this variable circumference. So if you think about having a line, right, and this is our linear function. This is what we want to rotate. If I were to rotate that about this x-axis, I would get a frustum shape, or rather kind of a piece of a cone. All right, so I'm rotating it about this x-axis. And what you would notice is as we move along the x-axis, the radius changes. That height or that distance from the axis is becoming smaller or greater depending on the direction that you move. So we have a variable radius represented by the function. And then the second piece here, the square root of the quantity 1 plus the derivative squared, that's my arc length formula. So all this formula is for surface area is the variable circumference times the variable arc length. Okay, circumference times the length around. So let's look at an example and see if that kind of helps us understand this better. And when we're in class and I've got time to really work with you, I do like to go into a little bit more of how this formula is derived. But for the sake of an online class, I'm just going to give you the formula and say, hey, this is how we use it. So let's do an example. In this example, we're going to find the area of the surface generated by revolving this curve, y equals 2 root x, about the x-axis over the closed interval from 1 to 2. So my surface area formula, remember surface area equals that integral from A to B. In this case, A and B are going to be 1 and 2. My formula is 2 pi times y. Y being this function, 2 times the square root of x. So instead of writing y, I'm going to write 2 square root of x. And then we have times the square root of 1 plus the derivative dy dx, whatever that is, quantity squared. Right? So it's pretty easy to look at this and set this up. We do need our derivative plugged in there. So y equals 2x to the 1/2, then dy dx is 2 times 1/2 x to the negative 1/2. Dy dx is x to the negative 1/2. Therefore, dy dx squared equals x to the negative 1/2 squared. Power to a power, you multiply exponents, that's going to be x to the negative 1. So this piece right here, I'm going to replace that with x to the negative 1 in there. And this is going to represent my surface area of the shape that will be created if I rotate 2 square root of x about the x-axis. And just before we actually get into our calculation, let's think about what this looks like. 2 times the square root of x, it's just going to be a taller square root function. And from 1 to 2, we won't need that piece right there. So it would be rotating this shape, it will be circular, about the x-axis. So we're going to have kind of this curved cone frustum. So now that we know what it looks like, we're calculating the surface area of that shape. Let's solve this integral. So the 2 pi and the 2 can come in front. That will be 4 pi. We have the integral from 1 to 2 of the square root of x times the square root of 1 plus x to the negative 1 dx. So we need to simplify our integrand, and using properties of radicals, these radicands, we can multiply them. So I've got 4 pi, 1, 2, and that would be x times 1 plus x to the negative 1 dx. And of course I can distribute that. So if I were to distribute that, I'm actually going to end up with x plus 1 under my radical. So I've got the square root of x plus 1 dx. So in order to solve this, we're going to need to use a u substitution. I like to think about that x plus 1 to the 1/2 power. So we will come over here and I'll say let u equal x plus 1. Then the derivative of u with respect to x equals 1, or du equals dx. As we work through this, we're also going to need to make sure we change our bounds. So we started with 2 and 1, or 1 and 2. I'm going to plug those in. U equals 2 plus 1, that will be 3, and u equals 1 plus 1 will equal 2. So I've got 4 pi, dealing with the integral. Now instead of 1 to 2, we're going to say from 2 to 3 of u to the 1/2 du. That's direct substitution, dx equals du. This is easy to integrate, adding 1 to 1/2. I'm going to get 3/2, so I've got 2/3 u to the 3/2. That would be evaluated from 3 to 2. I'll pull that 2/3 out in front. I now have 8 pi over 3. 3 to the 3/2 minus 2 to the 3/2. And that's pretty much my answer, but I can simplify those radicals. I end up with 8 pi over 3. 3 cubed is 27, and the square root of 27 is going to be 3 root 3. Minus 2 cubed is 8, and the square root of 8 is 2 root 2. And this would be the proper way to leave our final answer for this problem. And that's it. That's how you find the surface area of some shape created by revolving a function around the x-axis.